Okay, it's a pleasure to have Dubi Kelmer, who will tell us about
strong spectral gap for geometrically finite hyperbolic manifold. I'll write the title. Yes, first, thanks for inviting me to speak here. Close by. I will tell you about recent work, joint work with Pratyush, Sarkar, and Osama, Kahlil about this problem. But before I tell you about recent work, I want to give some history and maybe explain what is a strong spectral gap and what are geometrically finite hyperbolic manifolds. Well, I don't want to tell you what are geometrically finite hyperbolic manifolds, but I'll vaguely draw a picture. So, think of a hyperbolic manifold. You can think of n-dimensional, one-dimensional hyperbolic space, and you quotient by some discrete subgroup. And we want this, so here, gamma is the discrete subgroup, is an isometry group of the hyperbolic space. The group, the subgroup of the orthogonal group of signature n plus 1. And we say that the manifold is geometrically finite if the group is geometrically finite. And what it essentially means is that you can write a fundamental domain for this quotient, or precisely for, let's call this G, for G mod gamma, as a fundamental domain that has finite-sided fundamental domain, which is also a lie. It's a little bit more complicated than that, but let's just pretend that this is what it is. And just to have something in mind, let's draw pictures what happens in dimension 2 when n equal to 1. So a model for the upper space for hyperbolic plane, and this is a classical example of a fundamental domain for a finite area or finite group. This is one example. You can also have fact triangle group. So we think of the group generated a reflection over these three circles, and the quotient, the fundamental domain would be a quotient. I'm not going to talk about these. These are all have finite area. I'm more interested in infinite area ones. So what you should think about is, for example, fundamental domain that looks like this. So this was this is maybe the simplest typical example of what I would call a geometrically finite infinite index or infinite volume hyperbolic manifold. You have a cascade to infinity, and you have also these flares that give you infinite volume fundamental domain. And you also have some more simple things that is the same thing, but there's no cusp. What we call convex or compact. So when this talks, when I say, we actually just write down the words of what it is. So here gamma is a discrete subgroup, Zariski dense and geometrically finite. So these are the words. Describes setting that I'm talking about. And in this setting, I want to explain what is the spectral gap. So before talking about the strong spectral gap, I want to describe what is the spectral gap. So again, we are now always in this setting where you have infinite volume space. You still have the action of the Laplacian acts as a self-adjoint operator on L2 space, and using the scattering theory of Lax-Phillips, we know exactly how the spectrum of the Laplacian looks like in this case, and it is composed of a discrete spectrum. All the way to n squared over 4, and continuous spectrum from n squared over 4 to 50. Okay, so this is a people that if you're used to thinking about the finite volume case, where it's substance spectrum is more complicated, there you can have like embedded discrete spectrum inside the continuous spectrum. Here it is simpler. And we also know something about this, what is the bottom of the spectrum here. Lambda naught, at least under some assumption. So I need to introduce maybe one more parameter. It's called the critical exponent of gamma. So a priori, this is I'll just describe it in words. You can think of counting how many elements in gamma you have inside the hyperbolic ball. It grows exponentially. You can say, what exponent is this exponent? This is the exponent of how fast it grows. Okay, so this is the critical exponent. In general, it can be anything between 0 and n. But if it happens to be bigger than n over 2, then we know exactly what this lambda naught is. The lambda naught is delta times n minus delta. And we also, not only that, we also know exactly what is the corresponding L2 eigenfunction. So this comes from the Patterson-Sullivan theory. We can actually write down the eigenfunction corresponding to this eigenvalue. And then, yeah, I said I want to tell you what is the spectral gap. The spectral gap is just the gap between this lambda naught and lambda 1. Okay, and having control over the spectral gap is very useful in a lot of applications. For example, if you want to count again how many lattice points are in big balls, it grows exponentially. You know the exponent, and then if you want to estimate the remainder, the spectral gap exactly controls the remainder. And it also has very nice applications, exponential mixing, geodesic flow. The next topic. So, application. But before I describe this, I want to introduce 3 more subgroups that are going to be important. So we have inside my group K, which is the group of isometries, we have K, which is always going to be a maximal compact subgroup. We have K, which is going to be this one parameter diagonalizable group. And we have M, which is the centralizer inside K to A. And once we identify this as this orthogonal group, then you can just identify the group K as SON plus 1, the group M as SON, and this diagonal group, you can write it in parameter. Let's see what it is. And I also want to be able to identify, since this maximal compact is exactly the stabilizer of a point in hyperbolic space, so we can identify my manifold also as a double quotient of G with K. And if you want to look at the tangent or the unit tangent bundle of this, it's to the point here and a direction. And also identify it as G with gamma with n. And essentially, right here, the unitangent bundle, you remember one direction, but you forget about all the other directions that you can point as. You also have what's called the frame bundle, as if you want to also remember all the directions in your timing space, not just the one you're flowing in. So this is the frame bundle, which is just the whole homogeneous space. Okay. And it turns out that if you look at the geodesic flow is a flow on the unitangent bundle. You start with a point in direction and you just flow with the geodesic flow. And this homogeneous setting, it's given very nicely by this group action. Okay, so the action of this diagonal group on this quotient just gives me the geodesic flow. This quotient. And so sometimes if you read, you see the frame flow. The frame flow is exactly the same action. You just don't quotient by m. Notice that again the group A commutes with m. So this it makes sense for the group A to act on the left on this quotient. So now I want to explain the very basic idea of how having knowledge of the spectral gap can tell me something about rate of mixing. Again, if I start with any test function, just the test function on my manifold, I can decompose it using the spectral decomposition as a linear combination eigenfunction with these eigenvalues, plus something contributed from the continuous spectrum for the tempered parts. So I can write phi C naught plus C1 phi1 Ck plus, let's call this phi tempered, which is everything else that is coming from the continuous spectrum or whatever orthogonal complements the space span by these functions. And then if I want to look at what happens if I look at my test function, I apply the geodesic flow and the correlation with itself or with the different functions, I can expand this. These are eigenfunctions with different eigenvalues, so they'll be orthogonal to each other. So this decomposes as a sum of matrix coefficients of all of these things. And it turns out I have very good control. If I take phi to be one of those eigenfunctions, I know exactly how this behaves. Just maybe when I write this, what I mean is just integrate over my whole quotient space. Effects with this power measure of my group. And I also want to understand that I think of my function as a function of my manifold, but I identify functions on my manifold. I have this, I can identify x as this quotient. I can think of it as just k invariant function on G mod gamma. Okay, so first I start with a function on my manifold. I think about it as a k invariant function on G mod gamma. Then I can act on it, right? Otherwise, it won't make sense. In this section, I can act on it and I can decompose it. Like this, if I take any one of those eigenfunctions, these Vk are eigenfunctions of the Laplacians, and parameterize lambda k as sk n minus sk, which sk is something between n over 2 delta, with the 0 is exactly delta, and I might have some bigger eigenvalues. Then I can write this down. This is, I can think of this solves a certain differential equation. I can write down exactly what this function is a function of t, and I know exactly how it grows.
Yes, if you're working on Gmod gamma, you need to look at other representations as well.
Say that again?
If you want to do the mixing on Gmod gamma on your space that you've introduced there, then you have to introduce other representations, spherical stuff, which
this is exactly what
entry series. Oh, you're going to discuss.
I'm going to describe this. So this is maybe the baby case, where everything works out fine. I just use the spherical function.
Okay. All right.
And I know exactly how these behave. Decay is symptotic. It's maybe some constant e to the minus s. It decays exponentially. The exponent is exactly dependent on the eigenvalue, and the tempered part I also know exactly. It's like an upper bound. Constant e to the minus b. So if I combine this, let's even that makes life simple. Let's treat all of these things as just different error term. I get that for any function here, I get this. And even take two different functions. So I get some constants. It's just the inner product of my function phi psi with the base eigenfunction phi naught times this decay rate. Plus an error term which is exponentially small. This is and this is exactly what Peter was saying. If I want to look at the geodesic flow is on tangent bounded. So I'm really not looking at the right functions here. Right? If I want to say I have exponential mixing for the geodesic flow, I really want to take functions here, or if I want the frame flow, if I want the geodesic flow, these functions here. And then if I take a function which is not k invariant, then there's no reason I can decompose it as all these functions are k invariant. I need more functions as my space. So the way to handle it, as Peter suggested, is I need to look at the representation. I need to look at the representation. So the way to solve it is I think of the space into of G mod gamma as the unitary representation of G. G acts here on the right, and I want to decompose it. This again first decompose it into two parts. The tempered parts, and we call the non-tempered part. The tempered part is, I can say, it's characterized by the fact that it's tempered if I can bound the block of the matrix coefficients by fast exponential decay. Okay, so let's think of this is definition of tempered. There's some, I'm lying a little bit, there's some more qualification, but let's say this is tempered. So this is the tempered part. We need to understand what's left over. The good news is that we know exactly what are all the units for representation, or at least all the non-tempered ones of G. Okay, so, but this is a representation, it decomposes at least maybe a direct integral from the direct sum of irreducible ones. I need to understand what are all the irreducible ones. And then if I can control the decay rate of the matrix coefficients for the irreducible ones appearing in it, then I can control everything. Okay? Yes. So I need some background on what are the irreducible representation of this group. And there turns out we know we can classify it exactly. And non-tempered irreducible representation, there are a lot of them, but they are parameterized by irreducible representation of the group M that I defined before. Okay, so the unitary dual of the non-tempered representations are parameterized and hat, which is just the equivalence classes of unitary representation of this compact group M. And so the way it works is for any irreducible representation, I have a whole interval of representation that is I sigma, which is the interval between n and 2 and such that for any S in this interval, I have a irreducible representation that's called pi sigma S. It is an irreducible representation, which you see this is a kind of complementary series. So these are all the non-tempered irreducible representation I have with this group G. Okay, so these are all of them. I don't want to describe exactly what they are, but you understand exactly what they are. There are explicit models you can write down in some sense. I will tell you.
So to see has a nice feature. But there's only one complementary series. SL2C.
Yeah, in SL2C.
Kind of nice.
Well, SL2R is even nice.
Yeah, even nice.
For SL2C and SL2R, the things I'll discuss are things that are particularly nice. Things get a little bit messier. N is bigger than. Okay, but we know some things about them. First of all, when sigma is just a trivial representation, just two facts. If sigma is just a trivial representation, then these representations by 1s, then first of all, I sigma by 1 is the whole interval between n over 2 and n. And these representations by 1s contains spherical vectors. They have vectors invariant under the whole group K. And if you think of functions, spherical vector functions on the group that are invariant under K, it's just function on the quotient. Spherical vectors are eigenfunctions of the Laplacian with eigenvalue s times n minus s. You can identify spherical vectors with Laplacian eigenfunctions with eigenvalue s times this. Okay, so in some sense, these eigenfunctions that coming in from scattering theory exactly correspond to the spherical representations that are appearing in this decomposition. But now we have other ones, like we have now for any other non-trivial representations, we have more of them. If sigma is not the trivial representation, I don't get the whole interval, but at least I know that it is. It's contained in n over 2 to n minus 1. It's I'm saving here. I can write more clearly for a specific during the representation, I can write the explicit interval, but they're all inside here. And I also know that if you look at matrix coefficients, like any two vectors inside the representation space, it decays same minus maybe here. Okay, so the decay in a similar way as the spherical one decays. So the upper bound. Okay, so if I want to now do the same thing here, but now replace x with actually g mod gamma, is exactly like Peter said. What I have to do is I take a general vector, I decompose it into its, I think of it as a vector in an irreducible representation, I decompose it into the non-tempered part, the tempered part. The tempered part, everything decays fast, I don't really care about it, it's just an error term. The non-tempered part, I decompose it into whatever comes in there, everything that comes in here, I have control of how it decays. So if I can show that there is some interval between delta and something a little bit smaller than delta, where I have no representations with that parameter weakly contained in my representation, I will be able to bound everything else, like all the contribution of that. My buffer, and I'm going to get a result like this.
So something has D and something has M.
Okay, that's a good, very good point. D is equal to M. D is equal to N. Throughout this whole, like whenever I write D, this is okay. So now this brings me to the point of what is a strong spectral gap. This just was defined in a paper of Mohammadi and Oh, where they really wanted to show that they wanted to prove or to use exponential mixing, but not just for functions in the manifold, but for general function. And they coined the idea of strong spectral gap. I'll define it. This is from a paper of Mohammadi and Oh from 2015. So we say that gamma or G mod gamma is strong spectral gap. Yes, to condition one, there exists it's not smaller than delta gamma, such that now I sigma s with s between this not and delta is weakly contained in G gamma. And if I weakly contained okay, so the representation can be contained inside the bigger representation in the sense if there's an invariant subspace that you can identify this representation as a sub-representation. Weakly contained is a little bit weaker. It means that you can somehow approximate matrix coefficients of this representation by matrix coefficients in the bigger representation by choosing better and better values. Right? And the second condition, they also don't want the representation with parameter delta gamma to appear in this representation except at liberal. Okay, so we want that phi sigma delta by sigma delta is not in N G gamma unless sigma is a trivial representation, and then it is. But we have. So this is what it means to have a strong spectral gap. And again, that was their choice of definition. But I like this definition in the sense that a strong spectral gap is what you need in order to have exponential mixing.
By the way, what is, in principle, you could take phi to be an analytic have some analytic properties, and then the actual decay would depend on the poles of the scattering matrix, the Max-Phillips work, or more generally. And then you would need to, to say that tempered stuff is the best, you can't do better than tempered, would be secretly saying that you don't know that there's a gap in the poles. You know, have you thought about this? Whether there could be a gap strip of poles. Yeah, like if the group gamma were trivial. Take the free space. Then I think we know where the poles are. And I forget where the poles. I think they're on the imaginary axis. So you actually have to decay much further.
So there's.
You understand what I'm saying?
Yeah, I think so.
You're avoiding the question of where the poles of the scattering or analytic.
No, yes. So I'm here in the setting where delta of gamma is bigger than n/2.
Yeah, those are the first terms. But then when you get into the continuous spectrum, you're giving an upper bound of this decay. But I'm saying that may not be sharp.
Okay.
Could be better.
Could be better.
Because the poles may be further to the left.
Yeah, it could be better. Of course. So what I'm saying, but I'm not even getting close to that, right? Because
No.
I want to say that so this is in the paper they conjectured that every group with delta gamma bigger than n/2 has a strong spectral gap.
Okay.
This is the conjecture, and I guess maybe the result that I wanted to tell you about today is that we prove this conjecture. This is the states.
Okay, so we are always interested in there always being a guy above n/2, or delta bigger than
Yes.
that and all the rest.
Yes. So let me state that theorem. And this is again joined with Osama, Kahlil, and Pratyush, Sarkar. Maybe 6, depending if you're writing it, is that if gamma is geometrically finite, Zarinsky values with delta gamma bigger than n/2, then it has a strong spectral gap. So in their paper, they conjecture that you have this whole.
Is it true there are only finitely many? Suppose I give you.
Yeah, let me give you. So let me give you a open question that we still don't know, but we are working on. Open question. So this is the strengthening of this.
Max-Phillips show they only finitely many.
Yeah. So this is okay. So I'll give you an increasing order of hardship in terms of open questions. First of all, this is what I would call a uniform strong spectral gap. Is there some kind of uniform lambda? Let's say you can get 20. Let's see this, okay? Such that there are only so you can decompose L cube of Q mod gamma as a finite. So you have pi 1 delta naught, and then plus finitely many. Let's call it H S is SJ, where S1, so I'll just say it in words. So you have this finite, so inside HSJ, you only have complementary series with parameter SJ, but could have infinitely many sigma. And here you don't have any parameters below delta minus lambda. Okay, so you have some fixed numbers, so you have finitely many spaces, and then.
So this is only for n bigger than hyperbolic plane, hyperbolic three-space, no problem.
Yes, x and point. If I'm in n equal 1 or 2, this is true, and then it's something even better is true. I can take this to be the whole complementary series. Right, so if n is equal to 1 or 2, then I know that this is true. With this being the template part. Okay, and then the harder question, is it true in general when I can do this, or this is the template part? And this I don't even know how to show, forgetting the volume, even in the compact space. If gamma is so compact, I don't know how to show that this is true.
Yeah, I think you should point out the reason is that for each type, for each representation in, say, language parameters, for each representation of these types, sigma, then you would have any finitely many, but the trouble is that you want it uniform as you go.
Yes, so for this to be true, you need somehow for either, for some point, these sigmas don't appear anymore, which is what happens when n equal 1 and 2, all the for sigma non-trivial, everything is temporary. Also, you can also have something like this. If delta gamma is big enough, if delta gamma is bigger than n minus 1, you also have this for free. Because they're not tempered. But if delta gamma is small, then, yeah. So again, this is work in progress. I'm slightly hopeful that we'll be able to show something like this, but we will not there yet. Okay. So now I want to point out, I don't know, I didn't talk to either Emil or he about why they conjecture this, but usually when you conjecture something, you can either conjecture it because this is what you need in order to prove your theorems, and then you conjecture it true and you prove it demonstrably, or you have some reason to suspect why you think this would be true, which is, so one reason, at least that I think to suspect why this would be true, is that
was there in the case when gamma is a lattice already? Or
yes, okay, excellent point. If gamma is the lattice, then lambda naught is equal to 0. Okay, and then so lambda naught is equal to 0, or corresponding to, or like delta is equal to the edge to n, and then I know there are no complementary series between n and n minus 1.
Maybe you should in hyperbolic four space just draw the unitary dual.
Yeah. Okay. Yeah. So n is equal to 3. This is the first problematic point. The unitary dual, right? I have between 3 halves. 3. This is.
But it's indexed by 2 parameters.
2 is here. I have 2 parameters. So for each sigma, I have.
You should say it's a representation.
Yeah, sigma is representation of this time would be S. So sigma is just an integer. Right? This is just a Fourier coefficients. And for each, okay, so sigma, let's say m. So for each m, I have corresponding complementary series. M is equal to 0. That's the trivial one. Then the spectral parameters go all the way from 3 halves to 3. I can have for each one of them. I have. If m is not equal to 0. So I'm wrong. So this is sorry. Here, this I'm sorry. So that's SO3 in this case. So it's not wrong, but it's not integers, but it's representation of SO3. And for the trivial representation, I have this whole spectrum. For the non-trivial one, the complementary series just like here. So in the lattice case, the bottom of the spectrum is here, and I have a gap. So I might have finitely many spherical eigenvalues here from the it exists, but I have no complementary series, so there will be a gap. For the non-lattice case,
The point is that as you increase sigma, say the harmonic, defining the irreducible of your SO3, the interval doesn't shrink.
Yeah, the interval is always this one. So for all sigma, this is the interval, and I can.
So to say it's finite is to say that once you've got a very high at that oscillation.
If delta gamma is here, I have no control about so. And it's even more complicated. It's even more. So it's not even the case. So this is, at least as far as I know, it's not even the case that for a specific sigma, I know that I only have some finitely many. So as far as I know,
In the finite volume.
no, in the finite volume that is case, but in the infinite volume case, I don't even know.
Yeah,
It is probably true, but I don't even know that will just be discrete spectrum. Maybe there's a continuous spectrum.
My memory is the Lax-Phillips argument is very clever because it adds, wasn't there, you have to use its infinite volume. So they had to show, it's like these functions from classical, you have a holomorphic function which is got an angle bigger than pi, which it decays, and it's an entire harmonic function, then it's going to actually vanish under some assumption like that. That's what they're using. Point is they're using the free boundary in a clever way.
Yes, and I've tried to look at if the argument just generalizes to this, and it's at least as far as I can see, I don't see how to do it.
My memory is that they show there can be no eigenfunction supported in a sector. You know what I'm talking about?
Yes.
There's a sector, because you're square integrable, if you're going to be square integrable, you're going to have an eigenfunction which is decaying at infinity in the hyperbolic space. That sector is very powerful, and they use some Volterra equation. I can't. You should, yeah. I think you asked me this question.
Yeah, and I don't know. So the good news is that we find a way around. So I don't even want to assume that this is known. Right now, again, as in this case, at least I have an argument to showing that it fits up to between delta and delta minus 1, but I don't even know how to go beyond that. Okay, going back to my points, why did they conjecture this? Why did they suspect it would be true? So even before, so that paper was in 2015. Before that, already in 2011, exponential mixing for the geodesic flow was already proved using dynamics. And to do this, you need to actually using the how measure. It turns out is not the right. It's not the right thing to use. You need to use a different measure, which is called the Bohm-Margulis-Sullivan measure. It is the measure of maximal entropy for the geodesic flow. It is a finite measure, and if you use this as a result of Stoyanov, incorrectly. From 2011. Okay, so this puts the geodesic flow using this measure into the setting of axiom A flow, where exponential mixing is known. This for the geodesic flow, this if the quotient is what's called convex or compact, effects gamma is compact, then prove exponential mixing. So this is not with respect to the how measure, this is with respect to a different measure. Then the exponential mixing, the mixing looks like what mixing should look like, will just be the measure of the function. Divided by the measure of the space. Okay, so this is what you expect mixing to look like, plus and exponential error term. And in their paper, Mohammadi and Oh, I think that was the first part they appeared, they show that you can actually, this result, okay, first of all, this result holds for any delta of gamma. This doesn't depend, this holds when delta of gamma is smaller than n over 2 or bigger than n over 2. But when it is bigger than n over 2, what they showed is that this kind of exponential mixing is equivalent.
So does that use Dober here?
Yeah, this is the method of Tokyo Jet. Okay, so at least for the geodesic flow, you have exponential mixing, which if you have exponential mixing, this is kind of a very strong evidence that you have a strong spectral gap. And again, so this kind of exponential mixing is equivalent to the other kind of exponential mixing that this kind of exponential. So the natural question is, can you actually use the fact that you know that you have exponential mixing to prove that there's a strong spectral gap? And here comes another work of Edwards and Oh from 2020. Gave another proof of exponential mixing for the geodesic flow.
Okay, what's interesting is the methods of dynamics don't use Hilbert space. These poles, they're not, and the point of trying to use a unitary dual is the Hilbert space argument. So you're really controlling the poles. The poles I was talking about are also controlled there. To the left of NO2. Right. I don't know. But there's no obvious relation between the scattering poles that I know of and the poles of this Ruel zeta function, whatever is controlling them.
Yes, I also don't know the direct way, but let me continue with my chronological story to tell you about the results of the paper of Edwards and Oh. 2021, which gave another spectral proof or representation theoretic proof of exponential mixing for the geodesic flow.
There were old works of Peter Perry. We need to know about, which do relate.
These two.
The Eisens, and Patterson was also working on that, and Sullivan maybe also. The question is the poles of the scattering of the meromorphic continuation of the Laplacian, even and the poles of the Ruel zeta function, which is purely dynamic. And there is a relation, I believe.
In the finite volume case, it is the same.
No, even in infinite volume.
Yeah, we see. Okay, so let me tell you about Edwards. Oh,
I mean, I haven't thought about this in years, but that's my memory is that was they tried to prove the trace formula in infinite volume. So that, and they were, I know exactly what it is.
So
Used to be popular stuff.
So what Sam Edwards and Hill did, they wanted to prove exponential mixing, and we said we have these complementary series. We don't know how to show if they exist or not. But let's say maybe we can understand exactly how they decay. You can write it in this, so you can write it in a explicit model. And what they did is they actually write, instead of just saying an upper bound for how they decay, they made an explicit asymptotic expansion. And maybe to explain the result, I need to introduce one more topic, which is like for K types and M types. So if you take any irreducible representation of G, so if you take any by H, not irreducible, just any unitary representation of G, you can restrict it to the subgroup K or to the subgroup M, and then it just decomposes as a direct sum of irreducible representation of those smaller groups. So it's right by to K decomposes irreducible representation, and each one of those is an infinite dimensional space, but the compact group just acts on it as just this finite dimensional representation times this multiplicity space, which is an infinite dimensional Hilbert space. And we say that a vector in H is of K type tau if it falls in one of those spaces. So this is what I mean by K tau. And I can also restrict to M, and then I can say it is an M type. So then I can describe what is the theorem. Oh. One is if you take any two K types, the 1 and 2, one more thing we should put is a very useful observation about this irreducible representation. If you start with pi as one of those irreducible representations, pi sigma s, it doesn't have all K types. It has a K type inside it exactly if the representation sigma is sitting inside the representation tau. So let's have two K types. And you have any two vectors uv inside pi sigma s of K types, tau1 and tau2. Then you can write down the corresponding matrix coefficients as a main term. The decay is exactly how you expect the decay. P minus T times something explicit. Okay, so this is the Harshchandra operator. It's an operator acting on this representation. We know exactly what it is. And this is some kind of a unitary operator, not a bounded operator that sends vectors of type tau1 to vector of type tau2. What is this? 0. And then there's an error term. This is what they showed. But the more important part, that is the first part, this is true in general, that if those vectors u and v are also M invariant, then this thing is 0. The main term vanishes. Okay, so let's think about what this means. This means if you're looking at the geodesic flow, you're starting with M invariant function. You decompose it into the irreducible representations, you pick a vectors, all the vectors you get are M invariant, which means that when you look at those matrix coefficients, the main term vanishes and you just get the remainder term, so you get exponential mixing. And you don't need a spectral gap, right? Because even if they exist, they don't contribute anything other than their term. So this kind of put maybe think of maybe if this was the motivation for making this conjecture, question mark behind it. But in recent years, there been some advancement in the dynamical approach. So this is really things that have been happening in the last 3 years. The method of Stoyanov, or building up of your path, was extended to deal with, first of all, geometrically finite loops, so you can extend cusps, and also you can extend it from the geodesic flow to the frame flow. Okay, so this is the recent developments. So this is recent work of Sarkar and Winter, and also Lee and Pan, and also Lee Pan and Sarkar, all in 2022 to 20. We can extend exponential mixing and the frame flow in general, geometrically finite. so then I was at a conference last year, and I heard Pratyush Sarkar give a lecture about this, and he said, prove this. And then the natural question is, okay, so now can you use this to prove a strong spectral gap? And so now the counterexample of Factor O is not coming to play. And this is exactly the approach that we took. Now that you have exponential mixing for the geodesic flow, for the frame flow, we can use it to get a strong spectral gap. The problem is, again, that's how do you exclude these representations which are just weakly contained. So let me finish by a very, how much time do I have? Yeah, 6 minutes, enough. Just a rough sketch. The idea is, you do it. So the first thing, you can work one M-type at a time. Okay, so really what you want to show that for no M-type sigma, you have this interval that exists there. So you do it for one M-type at a time. So you fix, let's write something now. So in general, just using general spectral convolution, you can always write this. Parametrizing spaces, and then you have this direct integral over sigma. So let's H sigma S N. So this is some kind of tensorial measure that it's like an abstract concept. It depends on gamma, it depends on everything, and what it is. And then, so these are all the tempered, or the non-tempered ones, and then you also have the tempered ones. Okay, so we have this like general nonsense decomposition of my Hilbert space as the decomposition of the non-tempered part, the tempered one. And now the first observation is to prove a strong spectral gap. It's enough to show that there exists some S naught more than delta, such that this M sigma of S naught delta is 0 for any sigma. The point is that this S naught doesn't depend on sigma. That you have one interval, but the same interval works for all sigma, and these measures are always just 0. So now that you do it, you can just work one sigma at a time and just make sure that the interval you get is independent. And maybe also you also want to show that M sigma of
so for one sigma, you don't know how to run the lax Phillips argument. I take it back. It was not. It's not what I said. They added a compact operator.
Yes.
Their argument was to show that a compact operator after which everything is tempered.
Yes, I would. So this is my first approach was to try to do it, and it's not because I don't know. I wouldn't say it's impossible. I said I couldn't do it, but Lax and Phillips were much smarter than me. So I tried to.
That's how they did it. Now that I'm thinking, they added a compact operator,
compact.
and then they have only finitely many eigenvalues on it.
Yes. So, but the point is, my sense is
you try that with a sigma, or sigma is a finite compact.
Yeah. So my guess is that
it's
it
like
should work.
a vector bundle version of their function version. Yeah.
That it should work with a sigma. I just don't know how to do.
Yeah.
So the next idea is I want to borrow an idea from a paper of Kahlil and Guzel. They try to prove a spectral gap in a different setting, which is a non-homogeneous setting. And one idea is they use is to look at the Laplace transform of matrix properties, which is what we also did here. So use the plus transform. So we fix my test function. And we will take them to be of a fixed k type. And then, but for any two test function, you can define the Laplace transform of z, the integral from 0 to infinity, into the minus. Take the matrix coefficients and you get the Laplace transform. Just from just putting the trivial bound on how fast this decay, you know this converges when the way this is written here, this converges when the real part of z is positive. So the idea is that I want to be able to analytically continue it to the left, whichever you know. And what I want to do is use this decomposition. So let's assume now that if both phi and psi are some fixed data, I'll make some things a little bit easier. Then the only thing that comes up in the projections are sigmas that are contained in tau. So we can somehow decompose both phi and psi. Direct sum of all the sigmas that contained in tau, and the integral I sigma, and then that is sigma s. You know, this m sigma of s a priori is just contained, is supported on n over 2 to delta. This is where it's supported. And now I can use the analysis of Edwards and Oh. Right, for each one of those, this is in one of those representations. I know this one is a main term and an error term. The error term decays faster, which means that converge to the left of 0. So I write this function write this f of v. E of v. For inside A of z, I put in everything coming from the tempered parts, which converges everywhere. Also, the remainder term in the Edwards O analysis. The B of z is this explicit term, sigma tau, integral from this of the delta tau CFS. Sorry, so this first, like this, I know exactly how it decays, so I can actually execute this integral, and I just get C plus. Yeah. Now, this again only converges when the real part of S is bigger than 0, but it also converges to the left of that as long as Z is not real. Okay, so now I can analytically continue this. Z equals to 0. I have this extra strip, except that I might have poles on this line, but this is the only place I am allowed to have poles. And so this is now I want to add what I know about exponential mixing. The minute I add exponential mixing, well, I can't apply it to these, maybe to these functions. So I guess this is true. This is true for any function, but if I assume my functions are nice, again, there are some, let's say there are technical problems, but there are conceptual. The dynamical proof of exponential mixing, I can't just take functions in L2, right? I need to take functions to be nice enough. So, for example, smooth compactly supported functions, maybe some Kahlil continuous. But if I assume phi psi are, let's say, smooth compactly supported functions, in this space I can apply exponential mixing. Exponential mixing tells me that this function f of z is analytic in the real part of z greater than some minus. Let's stand it to the left with a simple pole at 0 coming from the main part. Great. So this is true in general. And now the hard part of maybe the technical part is to be able. Okay, so now I know even more. I know this is true for f of z. This is analytic, which means that this function now has an analytic continuation to maybe some smaller strip. Okay, coming from exponential mixing. So this function has an analytic continuation. And now there's a nice Stieltjes inversion theorem that if you have sine measure, I look at the real parts, I get a sine measure. And if you have an integral over a sine measure, and you can, a priori, it defines all the complex plane without the real numbers. If you can extend it continuously to an interval, that sine measure has to be 0 on that interval. Okay, so if you think about it conceptually, if this thing is non-zero somewhere, then I will get a pole. Right? The fact that I don't have a pole means that this thing is 0, which is what we used to show that this measure has to be 0. But to do this, I need to make sure that this is not 0. Okay, so the idea is, again, in the analysis of Edwards, this is very explicit. So the point is, for every sigma, I need to find the tau to make sure that this is non-zero on a positive measure set. Okay, so the usual part is for any sigma, you can find tau such that this matrix coefficient zero on a positive measure set. Okay, so this is done by analyzing exactly what is the formula for this thing. And if you're giving a sigma, you need to somehow construct with the right tau that will force this to be non-zero. And essentially exactly the opposite of what Edwards and Oh did, where they showed that this has to be 0 if you're M invariant. So then you can look at exactly the condition of when it is 0 and when it is not 0, and you can find for each sigma a tau will force this to be 0. And force you to have a spectral gap. Okay, so this is how maybe the I think we have to find shorts.
Forget the order guts method give any gap. Can you actually write down a number effectively,
Right now,
given
no.
all this data?
So we cannot write a number expected. So our number just comes with whatever
They give you, they'll
Yeah.
give you a number. and
we
you'll-
take a number. But what I'm saying is we are working on something that I think I probably believe this. So what I'm hoping, so we have another method that I'm hoping will be able to give something like this. Again, we don't get a number because we have these finitely many exceptions.
But you need them to get a number first.
No. So this is a different
Oh, a different approach.
a different approach. And again, I can say more or less what the idea is, but it's
Yeah, my memory is that Avila stuff is very hard to put a number. They're doing this type model. They're doing on the
Yeah.
strata, they're doing this mixing, which is very powerful in applications there. But experts tell me they don't know how to put any dependence.
no, it's very hard to put a number, but I think it should be possible to put a number that below which you have finitely many exceptions, and you have no control of those exceptions. So essentially, if you look at this picture, what the idea is, what you can show is that you have an analytic continuation, or you have a moromorphic continuation, when you can have like poles here, so you can have infinitely many poles. But on the other hand, because of this, all the poles are here, so there can be only finitely many. So this is the general idea. This is what they used in their paper, and what we're hoping is that to be able to do something similar here.
The difficulties are quite serious. If you take the higher rank situation, and you ask, is base class conjecture that Langdon's worked on and that eventually Bernoulli solved. These problems with the M types is exactly where you don't know. Say, if you want to count the number of eigenvalues less than X, Weyl's law, finite volume, higher rank, the upper bound is not known. It's known with the wrong exponent because the argument uses meromorphic continuation, and this is very hard to control in the M type, especially in higher rank, where you can imagine the unitary jewelers.
Yeah.
These are tricky questions, even in the finite volume. Very tricky.